everyone. You can hear me, right? Okay, great, perfect. So, well, he already did a very great introduction of myself, so I'm not going to go too deep into who I am, but another fun fact about me, before being a software developer, I've actually been a building architect before. So Madrid holds a very special place in my heart because you guys have one of the most beautiful and amazing modern architecture. So this is another reason why I'm coming to Madrid this time. And in case if you're interested, come find me to talk about architecture. So let's start with the obvious. What's the best place to get churros? Of course, I asked ChatGPT, LLM, and they gave me some very good choice. Maybe you guys can tell me whether they're actually good or not. Yeah. But one important thing about this is that this is not ChatGPT, but this is one on the web LLM. So what it is that it is actually a LLM that's completely hosted on your browser. So everything's hosted locally. You don't need to hit like an API. You don't need to hit the web. So everything runs locally on your browser. And it's free to answer your questions forever. So, last slide. So what is what is WebAI? So WebAI actually differs from Cloud AI in that it actually enables a lot of AI model operations directly within the browser. So it removes that need for any constant reliance on cloud infrastructure. So this allows AI models to run locally on your device, on the user's device for this high performance in-browser computation. So, and also another thing is unlike Cloud AI, it requires constantly sending all this data to remote servers for processing. It allows this kind of decentralized client-side execution. So it enhances a lot about privacy, latency, and then allows a lot of offline AI capabilities. And this approach, approach empowers a lot of browsers to operate as kind of like nodes in a distributed AI network. And all these models will run independently on a lot of devices while being able to share knowledge, updates, or insights across the network. So in case if you do also like DApps, this is also a very good use case as well. In case if you're building for any decentralized network. So why does it matter? So of course, the one core thing is price efficiency. So because if you run your AI locally in the browser, of course, it doesn't, you don't have that need for all this expensive cloud infrastructure. So it will drastically lower any cost for businesses and developers. And if you know, if you've developed a GenAI app, you know that there's actually a lot of cost. It really stacks up later on when you keeps firing prompts. So when you know that your infrastructure is locally hosted, you just don't need to worry about that cost. And of course, there's lower latency. Clarification. So of course, you still need to initially download your model and you need to wait for the model to be cached on the browser. However, all the subsequent prompts are actually much faster because again, everything's hosted locally. And one important part is the enhanced privacy. So if you're dealing with a lot of very sensitive data like patient data or finance data, then that privacy would also be very valuable for some use cases. So by WebAI, actually you basically need two core things to enable it. You need an open source model and you need a local computation setup. So I'm going to go into what local models there are. So what you see here are some of the you can say leading open source models here. They're capable of doing in-browser AI. So of course, they're not the most powerful ones, not the one that you can get on ChatGPT. However, these small models are the ones that makes it possible you can download and run all these powerful client-side AI, and they are specifically kind of trained for that. So for example, you have Llama 3. Everyone knows it's from Facebook, and there's also Mistral. They offer these basically these two models are they're very based on performance and speed, while there is Gemma, which is very ideal for these you can say low resource environments, so IoT devices or on your phone and so on. And there is also 5.2 and 5.3, which is from Microsoft, and they are more very light models optimized for these low resource environments. There's GPTJ. It's more, the use case is more for if you want to optimize for code. For example, if you want to do a simple weblet or something like that, then you can use the GBTJ. And there's also Red Pajama. So Red Pajama is it's very interesting. So the idea is that it will replicate Llama's capabilities, but the training data itself that uses it is completely open source. So if you want to build a model where, like, I don't know, if you're building something for research, you need to make sure all the data that is being trained is transparent data, then Red Pajama is a very good choice. And there are also some frameworks for these local AI. So these 3 examples here, they're not all WebAI. So for example, WebLLM is the one that I've just shown you. It's that one specifically for like hosting a package for hosting model in the browser, but the other 2, local AI and Open Web UI, is more like, a package or framework that allows you to ping a locally hosted somewhere on your local server or on your local machine, but it's not within the browser. So but I put them on here as an example, just as a comparison, if you are also interested to kind of spin up the LLM and spin up a separate server for your LLM. These are the other 2 options. In particular, so in this talk, like we will pretty much go below so there's, of course, you can just use WebLLM and you can pretty much discard a lot of the complexity underneath it. But however, the goal of this talk, we will pretty much go below the surface and explore what's actually happening under the hood of what WebLLM underneath the hood does. So it utilizes some core technologies like Wasm, WebGPU to enable all these like complex local inferencing. So this is the fun part that's underneath the hood. So what you see here is the kind of core tech stack that enables WebAI. So today, a lot of application developers and researchers, like when you have these machine learning researchers, they still build the models on a framework. So it's like us, we will build on React and so on. So they will still utilize a framework to build their models. And then all these models, they will require to execute on the browser using a runtime. So like TensorFlow.js is one of them. OnRuntime is another one where it enables those models to run within the browser environment. And then they use, these ones, they actually make use of these web APIs. So that's where they start to use Wasm or WebGPU to execute on the browser. And all these runtimes will eventually bottom out into running on the CPU via JavaScript or Wasm, or they will run on the GPU via WebGPU. So we can dive into the first part of that core web AI tech stack, which is Wasm. So a lot of application. So what is Wasm? So Wasm is a binary instruction format that's designed to execute code very efficiently on modern web browsers. So again, it enables near-native performance by allowing a lot of code to be written in like C, C++, and Rust to run in the browser. So does anyone here write C, C++ code or Rust code? Yeah, but if you do, that's how you get to run your code on the browser. And Wasm, one very important part is that it's very platform independent and it can be executed on any device with a web browser. So it expands the web's capabilities beyond JavaScript. Because in this case, like let's say if you write some very performant code in Rust, this is how you get it to compile and run on the browser. And the primary goal is pretty much like you can boost performance and provide that very secure sandbox execution environment. So in other words, like a lot of compute-heavy tasks like games, simulations, multimedia, all these applications, they will pretty much use Wasm under the hood. Like, for example, if you use Figma, they utilize Wasm under the hood. Yeah. So this diagram just very simply just illustrate how it compiles all these high-level languages from C, Rust, or C++ into a module that's executable on the browser. And from these high-level languages through the Wasm compiler so that it can be executed on either on the phone or on your local desktop. So why is Wasm good for WebAI? So the main core thing is because of speed. So Wasm will enable all these AI models to run with near-native performance in the browser. And it's very crucial for these compute-heavy tasks like deep learning inference. And of course, there's cross-language support. As I mentioned, they allow support across 3 different languages like Rust, C++, and you can run it in the browser without relying just on JavaScript, which is much more versatile. And also the main bit is portability. So Wasm code, it runs on any platform that supports a browser. So in that case, it runs on the laptop, it runs on your phone, it even runs on some, like on Raspberry Pi, anything that can allow a browser to be installed, then you can pretty much run Wasm. So you don't need any installation required. You spin a browser, you can spin up Wasm. And so what are the ways that you can utilize Wasm to optimize your AI models? The first use case a lot is people use it for model compilation. So you can compile all the AI models or part of that AI pipeline, like tensor operations or those model layers, using language like C++ or Rust, and then it can be optimized and run within the browser using Wasm. And of course, with Wasm, it allows a lot of parallel processing, because again, with JavaScript, single-threaded, once it hits the CPU, you can utilize true parallel computing. So it supports, of course, SIMD, single instruction, multiple data instructions. So it allows it to perform all these multiple calculations in parallel. So it's very good for AI tasks like matrix multiplications or convolutions in neural networks. And also another part is it can interface very well with WebGPU. So it can pretty much act as a bridge between all these high-level AI code within model processing or optimization algorithms and WebGPU. So if you write model-specific logic in C++ or Rust, if they want to utilize the GPU, they can via WebGPU, and then they can use Wasm to offload all these GPU-based calculations to WebGPU to enhance the performance. So in this case, for example, like in a real-time image generation app, so Wasm will pretty much handle all the model logic. For example, pre-processing of all your images or running matrix operations, while WebGPU will accelerate all those kind of heavier tasks like neural network inference. So you pre-processing all your images, get all the information that you need, and that's when you need to start doing all the inferencing, you can pass it on, offload it to WebGPU. So another example, what we have here is to use Wasm to run optimized models like TensorFlow.js with a Wasm backend. So this is a specific Wasm backend that TensorFlow.js provides, which significantly improves the performance for all these models compared to a default, let's say, JavaScript backend. So it's very useful for devices that doesn't have any access to WebGPU, or in cases where WebGPU is not fully optimized yet. So they can still allow you to run via Wasm to run only on the CPU. And as you've seen on this multiple slides before, on one of the first slides where I show you the tech stack of WebAI, so ONGS is that one-time engine that allows you to run all the models on the browser. So ONGS one-time is this high-performance cross-platform inference engine that's designed to accelerate the execution of a lot of ML models in the ONGS format. So a lot of machine learning engines, they might even develop models directly using the ONGS format. And it provides a lot of optimized performance on a wide range of hardware like CPUs, GPUs, and sometimes they even do specialized accelerators. So again, it supports Wasm. So it makes it very easy to run models trained in frameworks like PyTorch or TensorFlow directly in the browser. And Wasm will accelerate all this inference time by running all this compiled code much faster than JavaScript. Okay, so this actually brings us nicely to this next section on WebGPU. So before we dive into WebGPU, we need to actually look into why the GPU is very important for AI models. So again, the similar concept of CPU computing with Wasm is that it allows parallel processing, and particularly it's even much more powerful in that it can handle thousands of operations simultaneously, and it can accelerate a lot of AI tasks, again, like matrix calculations and neural network training. And in particular, GPUs are very, very good for trainings, and that is, with CPU, is incomparable. So it really speeds up the back propagation process and any other core tasks in deep learning, reduce training time for days to hours. So if your application, you would want to continuously train the model, then you pretty much GPU is what you need. And also you want to, it's very good for handling all these very large models, for example, it's very efficiently process all these large data sets and all these complex models like deep learning architecture with millions of parameters. And it's very optimized for a lot of AI libraries like, again, TensorFlow, PyTorch. They're pretty much built under the hood, they're built to leverage GPUs to maximize computational efficiency. And one very important part is how scalable it is, because with GPUs, you can stack them up. So it supports multi-GPU setup, so you can do distributed training, and there's a lot of faster model development at scale. And of course, if you're an environmentalist, it's also much more energy efficient. So when it comes to WebGPU. So WebGPU is a modern web API that's designed to provide a lot of high-performance graphics and compute capabilities directly in the web browsers. So has anyone in here used WebGL before? Yeah, so if you have pretty much now, other than using WebGL, you would utilize WebGPU because it offers low-level access to the GPU and enables you to write very much more efficient and powerful code for tasks like 3D rendering, AI model inference, and data processing. So it's really good for web games. So Again, the API is pretty much optimized for parallel computation, and it's very good or ideal for executing all these complex algorithms like ML models in real time and all done within the browser environment. So they bring this native-like performance to web applications without requiring external software installations or plugins. So here you can see these are some of the growing ecosystem of apps and libraries that uses WebGPU. So namely the most the one that everyone knows is Google Earth and Google Meet. And also, of course, if you build with Three.js, everything how the library utilized under the hood is all WebGPU. So what you see here, this diagram, pretty much summarizes how the WebGPU interface with both your web apps and your local GPU. Okay, let me get the... So there's several core concepts of it. So that's the native GPU API. So that is actually part of that is the native API that's provided by your operating system. So for example, if you're Mac OS, then it's called Metal. And it allows a lot of these like native applications, like for example, if you have Photoshop installed and so on, that's how they would try to access your local GPU. They do it via the native GPU API. So it allows all these native applications to utilize the GPU's capability by sending all the instructions via a GPU driver, via the driver here. And so while a lot of systems have like multiple native APIs, so most systems some systems have multiple ones, but the focus is usually you have one to communicate with the local GPU. And again, it enables you to utilize all the high-performance graphics and compute tasks to be handled very efficiently by all your native apps. So in web browsers, if you want to utilize the GPU, that's when you utilize WebGPU, which is this interface to communicate with the GPU through the system's native API and the driver. So this is pretty much how WebGPU does, is that interface layer. And the WebGPU adapter will represent the physical GPU and the driver on the system. So you can see here that the adapter is directly linked to your native GPU API, and it abstracts that layer. You don't even need to know how to communicate with that native GPU. You just need to utilize the WebGPU adapter, and it does all the work for you. That is the key part where it allows web code to access all the underlying hardware resources via WebGPU. And one very important concept is the local device. Logical device, yeah. Logical device is in the WebGPU allow all these web applications to access that GPU in a compartmentalized and secure manner, because you can have multiple web apps that still want to utilize the WebGPU, but each of them will have its own logical device to keep everything in a secure manner. And also there's logical separation while sharing all the GPU's capabilities with all the other processes that's on your computer. So what you see here is just a very, very simple example of how to set up WebGPU in a JS app using a WebGPU API. It's actually simpler than you think, but of course, how you ultimately send your items to the queue and so on still requires some higher level of understanding with GPU computing. But in this case here, you will pretty much, there's some core steps. You need to first request a WebGPU adapter. You need to create the device, which is that logical device that I've shown in the last diagram. And you need to set up, and in our case here, we've set up a render pipeline for drawing to, say, a canvas element on the main thread, at the main UI. So in this case here, you just basically, you can request a adapter and the device here via navigator.gpu, which will get that adapter that we've shown in the diagram before. And you can also use the request device here to request that logical GPU device for WebGPU operations. And then, of course, you need to set up your canvas, and you also need to configure it with the device so that it can be accessible by the WebGPU context. And then you can also set up all your pipeline setup to use, let's say, a vertex shader or fragment shader, whatever you want to draw on the canvas. And then the next bit is, of course, you just need to, whenever anything that you want to pass to the GPU environment, you need to create a command. So you create commands and you submit that to the GPU queue here. You create a command, and then that's how you start, submitting it to the GPU queue in order to, which the GPU will optimize and will carry out the process that you submit it to the queue, and you draw that. For example, in this case here, you draw that simple triangle with all the shader that you've configured in the command. So let's see WebGPU in action. So you might have seen this demo before, but this is one of the more famous one where it's Hugging Face demo of Meta's segment anything model, which will produce a lot of high quality object maps. So in this case here, you can, let me try to play, oops. So it will pretty much be able to extract a lot of object maps. So you can extract the dog, you can extract the grass, you can extract the tree and everything. And all this extraction is done via the browser, via WebGPU under the hood. So Hugging Face did a lot of benchmarks, and they've used this as an example to show how there's tremendous speed ups as compared to a CPU implementation of the same model. So let's say on an Apple M1 Max laptop, so the WebGPU was about 30 times faster. But if you're on devices where you have multiple GPUs stacked up, could accelerate the benchmark by even over 120 times. So it's much, much faster for some models if you use WebGPU. Oops. Okay. So here, this is pretty much kind of the summary of the differences between Wasm and WebGPU. Of course, they're very different things, but you can see how on the different use cases that they are, and they serve very different purposes within that web development, AI web development use case. With Wasm focusing on more near-native performance for CPU-bound tasks, while WebGPU obviously for this GPU-based rendering and parallel computing. So, in other words, Wasm is very good for general-purpose computation, enable applications AI. You can port, let's say if you want to port some applications that you've developed natively in Rust, C++, you can use it to port them into the web and support, on all those different languages. In contrast, WebCPU is pretty much, it's more suited for tasks that requires heavy graphics, rendering, or parallel computation. In a case like neural network, you pretty much need WebGPU. And they are, but both technologies, you can utilize both and integrate with JavaScript, but they are very specialized for different, you can say, performance needs of that AI model lifecycle, which I will actually go deeper into this in a later section in my talk today. So, have anyone heard of WebNN? Oh, okay. So WebNN is a very interesting API, and it's a very cutting-edge web API. So what is WebNN? So WebNN is a web standard that enables a lot of machine learning inference directly in the browser. So, and also it provides a lot of access to hardware acceleration like GPU, CPU, or particularly on specialized AI chips for much faster and more efficient ML computation. So this is a API that's more you can say developed by, between Google and Microsoft, and also particularly with Intel to work together with their specialized AI computing chips. But again, we can still use it. It's not like you need those very high computing power in order to use WebNN. Now, one cool thing is it allows a lot of access to hardware acceleration. So again, it has access to both GPU or CPU for these fast ML computations, and it's particularly designed to run all these pre-trained models natively in web applications. So as what you've seen here, web browsers can implement the WebNN API using a lot of native machine learning APIs that's available in the operating system. So you can see here, like, all these ML API. Of course, it's you can say that it's more on the later laptops. They have all these API under the hood, which the WebNN will have direct access to it. You don't need to you don't need to find a workaround to call these APIs. So you just use WebNN and you can get access to them. And so it allows a lot of these trades. Again, if you build a web app, you can tap into all these very cutting edge ML innovations within the operating system and hardware platform underneath it without you need to tie to any platform specific. So if you develop an app, you wanted to utilize all these native ML API, but at the same time, you also want it to be able to run on the typical laptop. WebNN allows you to configure that. And under the hood, it also have that flexibility to have different fallbacks to different, let's say if you don't have a GPU in it, it will allow you to fall back into CPU. So it's very powerful in that sense. So for example, in this case here, the WebNN graph will work very well with Wasm kernels in that, like, after perform let's say data preparation operations on Wasm, you can then offload any inferencing tasks on a pre-trained model to WebMN to do its best job with neural network operations and feed that results back to the Wasm kernel. So you can use Wasm to do all your pre-processing. Of course, you can dump it to WebGPU, but you need to know that lower level GPU computing. But otherwise, you can also put it into WebNN. It will do everything about inferencing, similar to like how GPU, because it can call the WebGPU under the hood. And then you can pass it back to your Wasm kernel to do the post-processing. So the WebNN API, though, is highly experimental. It's so it's in the candidate recommendation phase with the W3C as of now. Like literally 2 weeks ago, it's still it's still drafting to be part of W3C. So in case if you do play around with it, definitely you should have your say and try to contribute to it because it's developing rapidly, and I do see it basically have a much wider adoption very soon. So we've gone through those three technologies. So how does it all come together into building a WebAI app? So here I'm just going to walk through some different types of tasks within the AI lifecycle that can utilize all these different technologies for the different tasks. And they're you can combine them to maximize the performance or pretty much, basically assign different way according to how you design your WebAI app. And also you'll see some images like within the different lifecycle tasks. They're all generated by my friend, Dolly, so take it with a grain of salt. There's a lot of weird typos and so on, but it's more like, for fun, yeah. So the first part is when the application loads, the AI model, which is a neural network, is typically loaded you can load it in a Wasm module. So you can use it to load your model files and also handle a lot of the pre-processing steps. Like, for example, in this case here, you might want to use it to convert image data to sensors and pretty much prepare the model for inferencing. So again, Wasm has this near-native performance and portability, so you make sure that AI pipeline works really efficiently across browsers and devices. So in this stage, you don't need to call the GPU yet. But then when you start in this next phase, when you start, after you've loaded the model, you've done all the pre-processing of your data, and when you want to start doing inferencing, that's when you can start calling WebGPU, or in this case, you can also use WebNN. So you can use it to perform all these heavy, parallelized tensor operations like matrix multiplications and all that, complex stuff. And again, you use WebNN if you want to if you are loading a also pre-trained, a common pre-trained model that you pretty much, common pre-trained open source model that you can download from online, you can also use WebNN to load it. So And the next bit is you can also, if you also have any custom AI layers and operations, again, these are best to be done on, usually you can use it on Wasm or WebGPU. So for example, like some models, they might require some specialized layers, operations, depending on the model that you use. And then so Wasm, in this case, you can still use Wasm to handle the logic and the orchestration. So let's say you've done the inferencing, you need a special layer. You've done the inferencing, you push it to Wasm. Wasm can then orchestrate and decide whether you still need to do a special layer on it, and then you can put it back to WebGPU. For example, if you need a special compute shader, then you might need to push it back to WebGPU to define and accelerate some custom operations. So. Yeah, and then another part, and this is the core part where most likely the core bit of application, which is your real-time AI and interactive part. For example, you need to do AI-based image or video processing within your app. That's actually when you need WebGPU to accelerate all these tasks like object detection, face recognition, or style transfer. So because that's the part where you need large amounts of data that needs to be processed in parallel. And of course, you can also use WebNN to simplify and optimize these tasks by providing any AI-specific API that will automatically choose the best hardware of the job. So you can neither put it into WebGPU or WebNN if you want to, if you want a more high-level approach towards that running of that real-time interactive process. So this is the kind of the summary of those 4 steps. And this is an example workflow of a web app that will utilize all those 3 technologies. So first, you have your model initialization on Wasm. So for example, you load an AI model like a deep learning model for image classification is first loaded using Wasm, and you will start doing all the pre-processing, and then you do all the model execution, which is the inferencing process with WebNN. For example, you can use WebNN or you can dump it to WebGPU. You do the custom operations. So you get all your data. You can put it back to Wasm as the orchestrator. You put it back to WebGPU for any custom operations. And finally, you put it back to Wasm to do all your post-processing and all your results once the inferencing process is completed. Okay. So after seeing all that kind of in action, how you combine together, so this section mostly serves as kind of you can say some of the guidelines and some of the, you can say some of the guidelines when you're deciding which technology is suitable for your app. So I call it a decision framework, but it's some of the things that you can consider into what technology that you should use for the project that you're on. So again, this is mainly the summary of the core strengths. So as I mentioned before, Wasm, the core strength of Wasm is that it allows all this very high performance execution, and mainly because it's language agnostic. So it allows you to basically, let's say if you're working with a machine learning engineer, they develop a lot of code that compile. Let's say even in Rust and so on, that's very kind of optimized for this low level programming or native performance. Then it's pretty much built for Wasm. So while WebGPU, the core strength is that it has these next-gen graphics and computational APIs. So if you can get the latest GPU chips, you can use WebGPU to utilize that computing power. And of course, with WebNN, the core strength is that it's a very high-level API. So it can, and it's mainly designed to simplify machine learning inference on the web. So it's, in this case, you just only need to know, you don't need to know a lot of the detail and the lower level GPU computation or how you would utilize Wasm. So you can just use WebNN to abstract all that complexity. So in this case, it translates very easily to use case. For example, Wasm is very good as doing all this, you can say just computationally heavy tasks, but such as pre-data processing that needs that efficient CPU execution. And for WebGPU, it's mainly, that's actually the core use case. If you need training, you need WebGPU. So if you have a model that you want it to continuously train on your user data and so on, then you will need to utilize WebGPU. WebNN doesn't allow you to do training because WebNN mainly allows you to load pre-trained models that you will continuously execute on that previously pre-trained data. But if you want your application to enable to kind of evolve by learning user data, you will need WebGPU. Yeah. And again, WebNN, if you want to run all this, it's a quick solution you can download. There's a lot of pre-trained models, and then you can just pretty much use WebNN to utilize that. And one very next bit is important bit is also you need to consider your AI ML requirements. Again, as I mentioned earlier, if you need training, you pretty much need WebGPU. If you're just simply inferencing, then you can just use WebNN. You don't even need to go into all that logic about GPU computing. And also your model size. WebNN still it's like if you have more lightweight models, then you can just use Wasm. You don't need to offload anything to WebGPU. However, if you have large models, you pretty much need WebGPU to leverage all that full power of parallel computing on the GPU. And one very important thing when you're developing your app, you need to really analyze and think about your target audience's hardware and the environment. So if your audience are running, I don't know, on the latest Macs and so on, then of course, you should utilize all these like high-end GPUs available. You can do all this learning, all this training data, you can utilize WebGPU. However, if there's a lot of unknown or uncertainty on the hardware, then actually WebNN is a very good choice because it will adapt to the different hardware and provide a very good balance of performance abstraction. And you don't need to configure that. They will do everything of that for you under the hood. And there are a lot of cases where you know that it's a CPU-bound environments. Like, I don't know, like if you're targeting some, let's say like phones or something that you know that there won't be strong GPU power for the device, then pretty much Wasm is the only option that you have if you want to have that performance boost. And of course, another thing is also you need to consider the cross-platform performance. Again, Wasm is the best because Wasm is the most highly adopted. Like the typical browser will run Wasm, while WebGPU and WebNN as well will need something very much on the cutting edge. You need everyone to have the latest version of Chrome Canary to do it. So that's another catch-all of WebGPU and WebNN. And one very important part, of course, you need to think about your development effort and the learning curve. So I'm going to be very quick on this section because the main thing you can already see, like Wasm, you have a lot of low-level control and performance, but it's always we have lots of control comes lots of time required to maintain it. So you pretty much need to do a lot of manual work to optimize all these AI ML libraries. And the same thing with WebGPU. It's on similar spectrum where you need to, it has a steeper learning curve, especially if you're not very familiar with GPU computing. You need to think about how you send all these processes to your GPU queue and how to optimize it. And you might need to look into how GPU will do all that parallel processing under the hood. But with WebNN, it kind of abstract all that stuff. You don't need to worry about this. And the other part is you also need to think about the existing tools and ecosystem. So Wasm is also widely supported, widely available, and especially if you're working with, let's say, a machine learning engineer, they might have developed something on PyTorch and so on. Then it makes sense to use Wasm as that kind of layer to allow to port it to be available to be used in your web app. And with WebGPU, it's actually relatively new. So there's a growing ecosystem, but it's not that widely supported. So you might need more effort into looking into resources to, when you develop with it. And it's the same with WebNN. But WebNN is still much easier because it already integrates with several very popular AI libraries and models, like again with TensorFlow, JS, or ONS. So it's a much easier path. It's just like utilizing a simple web API. You don't need to know all that low-level stuff under the hood. And another part, again, the use of AI library. If you're using something custom, you develop it with a machine learning engineer, you pretty much have no choice. You pretty much have to use a Wasm kernel, Wasm, to compile it into something that you can use on the web. And in WebGPU, if you're using, sometimes you're using AI frameworks that are like more optimized for WebGPU computation. Like, I don't know if anyone use XGBoost or if you use MediaPipe, for example, then WebGPU would be, they will pretty much require WebGPU. But again, it requires a lot of manual work if you want to configure the usage of WebGPU with those APIs. And WebNN, it's popular framework again, but you can only utilize popular framework right now with WebNN. And also you need to consider your team's development stack. So in Wasm, if you're working with a lot of backend engineers that will use Rust, will use C++, and so on, then you have someone to help you support that, then you can actually really consider Wasm. And with WebGPU, if you also want to like, if you want to, let's say if you combine this with like games and so on, like if you're using Babylon JS and so on, then you can also work together with things that you're building, like these highly interactive things, then you can actually utilize WebGPU. And of course, with WebNN, the typical web developer, that's how you should start with WebNN. Of course, there's a lot of future-proofing and long-term maintenance, but in short, Wasm is, you need constant maintenance because everything is very custom, versus WebNN, it's a growing, it's basically a web API that's continuously developed. So there's less upkeep if you're committed to WebNN as compared to like Wasm, you constantly need to maintain it. So, okay, so this is the overall use case. I know I'm running out of time, but if you're interested, you can take a picture of it and, use this as the framework when you consider, use these three technologies down the line. So I want to start end my talk with the AI PC. So this is something that Intel has just released, which is a very PC that is particularly to empower WebAI applications with this incredible on-device processing power. Like they have the NPU, which enable all these advanced AI tasks to operate directly on personal computers. And it's not going to stop here. It's just only get stronger and stronger. And as web developers or as the developers, as a typical developer, we also need to take that into consideration. And I can guarantee you, any application that you develop, let's say 3 or 4 years from now, you will need to consider WebAI or edge AI computing. And this is the kind of like full picture of the current WebAI ecosystem. And and again, there's a lot of these different use cases, one-times web APIs, etc. So we are pretty much only at the very beginning of this journey from transitioning from the normal web app to WebAI. And as this hardware advances, the potential for WebAI is pretty much limitless. You can pretty much do anything that you want. You can build a custom model for this custom task that you want to do with your WebAI. You don't always need to ping OpenAI. So it's pretty much, I think we're in the edge of another revolution from Web 3.0 to Web 4.0 with web apps that come fully embedded with its own AI model for any specific use case. So encourage everyone to be one of those pioneers that shape the new Web 4.0. It's a very new field. It's you can say it's a Wild West, but we definitely should be one of the pioneers to pioneer this because it's just going to be an ingrained part of the development process, no matter whether you welcome it or not. So that's it. That's my talk. Thank you very much. I know that's a lot of information to digest, but I'm not very much on X now, so add me on LinkedIn if you want to continue talk. Yeah.
The first one that I got in the list is from Angel. Are there any successful use cases for distributed model training using WebGPU and P2P networks?
B2B. Okay, so I haven't seen any very, very widely adopted use case. I think there will be one coming very soon. But at least from what I know, there were some people experimenting with, for example, how small models, we're experimenting text detection, where you want to filter out keywords and so on. These are the kind of use cases that I know is very good for these on-device models, where you don't want to always ping the internet every time. You can use, if you want to do offline first, these are the things where you can utilize a small model that can be trained for a very specific use case. Yeah.
Okay. Christian is asking, do you have real cases where WebGPU can be applied?
Oh, actually, there's lots of cases. WebGPU is, I'm talking about it in the application of AI here, but it's something that is, I would say, like more in domain of web games. And of course, Figma is one of the biggest utilization of WebGPU. They haven't released about how they configure it under the hood, but I know that they utilize it. And of course, what we see here with Google Meet and so on, anything that requires video processing, they will pretty much try to utilize WebGPU under the hood.